Okay, here we go. So, here's the devotional to go with that music. Jesus came and said, all authority is given on earth has been given to me. Go out and make disciples of all nations. Teach them to obey everything I've commanded you. And surely I'm with you to the very end of the semester. Yes, that's what it says. So let's hope we get to the end of the semester here. And the new age will begin. They're called the summer age. Yes? Mm-hmm. Right? Called the marriage age, says Hoyt. Called the graduate school age, says Ball. Yeah. We call the meteorology age, says Glenska. Yeah. All right. So anyway, in all these things, hopefully we can last through our age here. Let's hope that we do. Let's pray that we do. Dear God, be with us as we disciple ourselves, we self-discipline ourselves to make it through this age, this period in our life, this semester. Help us to stay on track, be organized, get things finished when they need to be finished, do our best to complete this age, a sprint to the last line. In Jesus' name we pray. Amen. The student said. Amen. Okay. So, here it is, the way, the truth, and the life. So we are 24th of May. Yes, on our journey through physical chemistry. I shouldn't have class after lunch. Yeah, this is too hard. Mm-hmm. Yeah. Anyway, here we go. So, test on Wednesday. Today we'll finish up a couple things on heterogeneous catalysis. See if there's any student presentations, stuff like that. And then we'll have our test on Wednesday. Friday will be our final review over anything that comes up on the test. I'll get you your test back by Friday, if not before. And then you can do your revisions of test number 4 and bring those to the final. Okay? And the final is scheduled for Wednesday. No, Wednesday is our test. Let's see. Final is exam scheduled for Tuesday, May 2 at 12:45 p.m. here. Yes? And so your test revisions are due at the final. Note that your reading in science is due on Friday. Your response to a little book by Zelazny there. Yes? Which you've all been enjoying reading, I'm sure. Yes? Thursday, science seminar. Pharmacology guy coming, talk about pharmacy stuff. So you want to check that out. See what's new in the world of drugs. Yes? If they got drugs to cure your addiction to other drugs. Yes. And you get addicted on those drugs. So it can be, that way they can keep the pharmacy business going. Right? Shouldn't be so cynical, right? Okay. Stuff like that. So, make sure you got your schedule worked out. Know where you need to be when. Know what has to be due when. Right? Because we're coming to the end of the age. Right? It's like the restaurant at the end of the universe. If you run the Hitchhiker's Guide to the Galaxy, nothing after this. Right? So if you don't evacuate the restaurant in time, you're going to end with the universe. Guys ever read those books? Hitchhiker's Guide to the Galaxy. There's like 3 of them, I think. Yeah. One of them is a restaurant at the end of the universe, where the whole universe blows up. Right? And you can watch it, from the restaurant at the end of the universe. But of course everybody has to get out before, get back in their time machines and go back. Right? Because otherwise you live through the end of the universe, and that's not good. Right? Yes? So you hope that your time machine is running right. It doesn't have a misfire or something, because you don't have time for repairs. You're at the restaurant at the end of the universe, right? So there you go. That's where we are now. We're sitting at the end of the universe here, at the end of the age. The age is coming to the end. Yes? Mm-hmm. Have I said that yet? The age is coming to an end. Semester is coming to an end. It's almost done. Yes, this week and next It's all over, for good or for bad. Okay, if you can't make the Tuesday time, you can come join the general chemistry students on Wednesday morning at 7:30. If you want to do that, let me know. Okay, let's see. Glenska, you the one taking the exam? Other two, I don't know, do you? You figure that out yet? I guess we'll know after test 4 or something, huh?
So what determines?
I think you have to have a B in the class and a B average overall. Doesn't know until the last test, I guess. You got a 0 on the test 4, it probably wouldn't be a B anymore, huh? That'd probably hurt you. It's 100 points there. Yeah, it's got to take test 4. All right, bummer, he says. Yeah, no breaks. Nope. Okay, so that's all that stuff. All right, last time we were together, we talked a little bit about heterogeneous catalysis. Right, we reviewed some collision theory equations. Remember the collision frequency with a wall, ZW. We talked about the units involved there. Okay, testing them out. I think your homework has some homework problems for you to do. Calculate those things again. Keep you updated on plugging and chugging, putting numbers in there, putting them in the right place. Okay, make sure all the units follow along. Okay, and there you go. And we talked about characterizing a surface using different types of spectroscopy, right? X-ray, photoelectron spectroscopy, or ultraviolet UV vis, photoelectron spectroscopy. You can use some other methods too that your book talks about. Those are the two big ones. You can talk about AFMs and SEMs and all that kind of stuff too, if you'd like. All that stuff is in there for characterizing surfaces. Yes, and then we talked about the adsorption, the adsorption and desorption on surfaces. And when we look at that a little bit more here, we'll see how that leads us to isotherms and equilibrium coverage. We just got to the point where we introduced to you the idea of putting stuff on and taking stuff off. So we'll finish that little story here after the break. Yes? Right? Because we need to have a break because, man, I just had lunch. I didn't get a nap in, right? So, kind of lagging here, right? So here's our surfaces, okay? Here's some vocabulary for surfaces, right? Steps and terraces and kinks and all that kind of stuff people talk about on surfaces. And depending what angle you cut through your unit cell, you get these different patterns, like you see up on the top there. And we'll have the 111, the 100, and things like that. It all depends on the slice that you're taking through the unit cell. And there's little ways to calculate what those are, right? Actually, I took a diamond along. Okay, totally that. So all that stuff is good. I think you guys know all those things you can read about. Those exciting things there as you go forth. Oh, here's one we didn't talk about. Low energy electron diffraction. Yes? We use electrons instead of photons to characterize surfaces. That's called LEED. Yes? Let's see. Oh, and then we could take coverage here. All right. So then we talked about, here we go. Here's our Auger type stuff. Yes? Where, you take your X-rays, come in. So this is your X-ray photoelectron spectroscopy, XPS. You can call it XPS. Right? Sounds like a trim level on a Ford pickup or something. No, that's XLT or something. No. You don't have Ford pickups, White? No. You're a Chevy family, are you? You don't have pickups? You live out in the country, though, don't you?
Yeah, I have those kind of.
Oh.
It's like Texas country.
Oh.
Yeah.
So you're like urbanites living out in the country, huh?
No, we're not urban.
No, you're not urbanites?
No, it's like this.
You got animals?
No.
No, well, okay.
We live in the middle of the
Middle of the field? There's
Farm
trees.
life without
Is there
the
trees
farm.
around the house?
fields. Right.
Yep. Any trees around the house? Okay. Well, that's all right. Okay. But you don't farm yourself. You just live out there. Okay. All right. So here's the idea. You knock this electron out from the bottom here. So there you go. You knock him out with an X-ray. And then this electron here falls down to there, and he sends out this photon as he goes out. Yes, and you can acquire that photon in a spectrometer, measures wavelength, its energy, and stuff like that. And that can tell you something about, this energy gap here that you're filling in. Okay. The other thing is, you could have this electron lose some energy, yes, but instead of falling down, instead of its energy going out as a photon, it sends some of its energy into knocking this other electron out over here. And we call that a secondary electron that gets knocked out. So you might get a photon, but you also get the secondary electron, and you can measure the kinetic energies of those secondary electrons. And so when you do the SEM type stuff in your forensic microscopy class, you look at secondary electron effects as well as photons that are being emitted from your surface as you do these things. Right? Okay. All right, so all that stuff is good. You guys can read through that. Chemisorption and physisorption. I'm not sure if we talked about these, but they were on the test when I wrote them, so I thought I'd better talk about them in lecture here. All right? Hint, hint. Okay, so physisorption is when you physically adsorb to something. So these are physical bonds, you might call them. They're long distance. Yes, van der Waals type of interactions that a molecule has with the surface. Okay, so we're talking, 4 to 5, maybe longer angstroms. Yes, so van der Waals type distances between the molecule and the surface. Weak stuff, so you're talking about maybe 10, maybe up to 100, if you got really strong ones, joules per mole there. Where chemisorption is when you actually form a chemical bond, right? Chemical bond. Yes, between whatever your substrate is and the surface. Okay? And of course here you're talking about hundreds of kilojoules per mole, yes? And you're talking about distances of maybe an angstrom or so, the distance of a chemical bond. So chemisorption is probably, 1,000 times stronger than physisorption, yes? Physisorption is just barely hanging on. Okay, how many of you feel that you're physisorbed to this semester? All right, how many people chemisorbed? Anybody chemisorbed? No? Oh, Hoyt is. She's got this all under control. Yeah, okay. All right, so there you go. So know the difference of those, and this is in that descriptive part, was it chapter 23 or something, of your Atkins book. So do read through some of these things. Don't just hunt through for the equation of the day and the example problems. It's helpful to, sometimes read the text here in this chapter. Some of Atkins' text isn't that well understandable until after you understand things, yes? But this little chapter on surface chemistry is readable. You can kind of read through it and it can kind of make sense to you. All right? Okay, so those are some things to note. Okay. Let's see, do we have any student presentations today? Oh, we do? Okay, well, looky there. All right. We have some student presentations. Let's see if I have some student presentation forms somewhere.
Oh boy. Yeah.
Oh, good. I do have some.
Didn't go test it as I wanted it to for a couple reasons, but it worked better than it was previously. It wasn't fine the first time.
Student presentation evaluation form for you. Pizza, spaghetti, ice cream. That's not good stuff.
Okay, ready?
Okay, let's do it.
So my problem comes back from the previous homework, 33.
Oh.
the problem that I was trying to present previously and could not due to some error, which I never really identified the reason for, but when I rewrote the equation a couple times, it finally worked. So the problem set is talking about the interaction between two helium models, and it gives some experimental data that's been recorded for it, and tells you to determine the Leonard-Jones parameters, which are Rho and epsilon, and plot the Leonard-Jones potential for the helium-helium interactions. And then part B wants you to plot the Morse potential given an A value. First, for the Leonard-Jones potential, I found that nice formatted equation there, but they use sigma instead of R0, but it's the same thing. And then you just find your epsilon is equal to your HCDE, which was given to you as an experimental value.
And what units do you have for energy on there?
Joules.
They're about 10 to the minus 25 or so?
So I should put a space there between that. It's the 10 to the minus 23rd joules.
Okay. So if you multiply that by a mole to get on a per mole basis, you have about 1 joule per mole or so. And that's about the depth of your weld. So for these long distance Leonard-Jones type interactions, you know, you've got just a joule or two of bonding energy. And that's 300, picometers? So that's about 3 angstroms at the bottom of the well here. So 3 angstroms, long distance, yes? Long distance, weak bond, right?
Yes.
This is just this multipole interactions, which is why you got these 1 over r to the 12, 1 over r to the 6 type things. So lots of good stuff there in that Leonard-Jones equation. And epsilon is equal to what?
It's the depth of the well.
Depth of the well. Don't confuse it with the permittivity constant, right? Which is also epsilon, right?
Right.
Yes.
Right. And then you also solve for RE using, R0 using RE,
Okay.
which is given there.
Yep, and there's a nice equation from R0 and RE. So R0 is equal to RE times 2 to the 1/6 power. Okay?
Did I
You got
leave something out there? Oh, I did. There's supposed to be a negative here. Because that one's positive, this one's supposed to be negative. Exponent.
Ah,
Yeah.
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 okay.
Thought I put that.
Okay. All right.
Indeed.
Okay, and the Morse potential.
And you get the Morse potential. And I wanted to put the two graphs together, but the program I was using wouldn't let me graph them at the same time. I could have put them next to each other, but the problem is the Morse potential is much more steep in the left side, so it scales up much higher on the field of view.
Well, it flattens out your Leonard-Jones potential.
Yeah.
Because
Because like they end up at the same bottom point here, but the Leonard-Jones curves out gently. Well, this just goes straight up.
well, your Morse potential is a lot deeper too, right? Should be a lot deeper than your Leonard-Jones potential.
Should it be?
It should be. Let's see. Yeah.
Well, I forgot.
This
The
is
way
like
that it,
10 to the minus 23rd.
I forgot the way that they had. I forgot they left out the part of the equation here that I used because this also has the way that the problem tells you to do it is not only having the HCDE here, but also subtracting it here so that it does have the same bottom as. So you set them equal to each other at the bottom. Just the
Well, the top should come up a lot higher.
yes,
Yeah.
and it does. Although you can't really see that, but this is a much more gentle curve there.
Well, look at the scale.
Well, yeah, that's what I'm saying. The scale of this shows much.
Your last quiz. Yes. The end of the age is here. Okay. There we go. Last quiz. No quiz on Friday, party day. Yes. My key. It's just algebra, guys. Be careful with your algebra. Yeah, you want to get something in the end that has just k's and p's and thetas in it. That's a big clue. Yep. What happens to the end? Yes. About another minute or so. You can finish it up. Okay, so here's the math, how this works. You know, well, you move it over to the other side. You got to add them together, and they're going to equal 0, right? So the rate of desorption plus the rate of adsorption is going to equal 0 when you get to a steady state. Yes? Mm-hmm.
I will just set them
going away.
equal to each other.
Yeah,
Oh.
No, you got to add them together equals 0. Some is coming and some is going. Yes? Right? So the coming is a positive because the fraction is increasing, fraction is covered. The going is a negative because the fraction is, you know. Oops, that probably messed things up, huh?
Yeah.
Oh, shucks. Okay, so you set them. So you got this plus this equals 0. Then this equals that. Yes? And then you combine these like terms as best you can. You got thetas here and thetas there. So you put all the thetas on one side, and then you can see that the ends are all going to cancel out. Yes, the ends all cancel out. And you get just the KD and the KAT times this thing. So you take that divided by this stuff. And if you want to get it in terms of the K, or K is equal to KA over KD, you take this KA divided by KD, and these guys divided by KD. So K divided by KD, and a KD divided by KD is just going to be 1. KA over KD is the K, and another KA over KD. All right, so anyway, 3 points, extra credit, right? If you messed it up, oh well. No points extra credit. Not going to kill you. But,
You gave it your best shot.
yeah, this, you know, I mean, put it on a quiz, and it's a good exercise, and algebra and steady state type stuff and things like that. But this also leads us to what we call the Langmuir isotherms. Okay? Right? So we get this thing here. This is called the Langmuir isotherm. Okay? And these Ks, these are equilibrium constants, right? Kas over Kds, like your equilibrium constant. And we know that each one of these guys, Ka and Kd and the big K, all these guys are going to be a function of temperature. Yes? Equilibrium, we know, is a function of temperature. Your equilibrium constant changes as a function of temperature. Yes? And so also the big K here is respect to the equilibrium of the amount of coverage. Remember, this is just a fraction, someplace from 0 to 1. This theta is a fraction of your coverage. Yes? And so we call these isotherms for a particular K. So here we go. So here, your Langmuir isotherms. K is a function of temperature, right? And so it changes as a function of temperature. So here's our different Ks at different temperatures. Yes, here's pressure. Pressure is in here. Yes. And then the fraction is over here on the y-axis. So it's a fraction as a function of pressure for a given K. And Ks are calculated based on a temperature. Yes? That's why we call these isotherms. So here's your fraction as a function of the pressure for a given temperature at which the K is equal to 0.1. Right? So you do surface chemistry type stuff, yes, and you know what the Ka and the Kd is, right? For a given temperature, you can calculate what the big K is as a function of temperature, and then based on the pressure of your system, okay, here's the pressure in atmospheres, you can calculate what your coverage is going to be. You can see that it approaches 1, asymptotically, might not get there, or approaches that as you go to higher and higher pressures. Yes? That's your hope. Right? Yes? So we call these isotherms. Right? And you have some homework problems there to compare things at different isotherms. So for this particular reaction, for this particular Ka and Kd, and it's different for every different system that you have, yes, you can see that as the K increases, you get better coverage. Yes? Now we're talking about monolayer coverage here. We're assuming that you're not building any islands or mountains on the surface, that everybody's going down where they can on the surface site. Truth is, that doesn't happen very nicely, right? Usually you build mountains and stuff. All depends on what kind of stuff you're trying to put on what kind of surface, how easy that goes. Some things are clumpier than other things. Yes, silver can be kind of clumpy if you're trying to put silver on a surface, depending on what the surface is. All kinds of interesting thermodynamics go into those Ka and Kds and stuff like this. So we're just kind of scratching the surface here of these things. Now there's another thing that we call the Van Hoff equation. Van Hoff had lots of equations, so this is, we have to say, this is a Van Hoff equation for isosteric enthalpy of adsorption. Okay? And it looks something like this. It says that the partial derivative of the natural log k, that's your big K, your Ka over Kd, okay, with respect to temperature at a constant pressure is equal to the delta H of adsorption divided by RT squared. Okay? So this is the Van Hoff equation for isosteric enthalpy of adsorption. Yes? So if you know what the K is, and if you know how the K is dependent upon temperature, if you have an equation for that, you can take the derivative of the natural log of that equation at constant pressure, and from the slope of that, you can get the delta H of adsorption. Okay? So if it's physisorption, that delta H is going to be small, right? If it's adsorption, the delta H of adsorption for chemisorption is going to be much larger. Yes? And you can have your intuition of what that should be as a chemist. Hundreds of kilojoules for chemisorption, tens or so joules per mole for physisorption. Yes? And you should be able to plot these things up, right? And then there you go. So if you plot K as a function of T and then take the derivative of it, you get delta H of adsorption over RT squared. And I don't know if your book gives you a justification for the derivation of this, but it's very similar to some of these things that you did for Arrhenius plots way back in the old days. Except now you got the Ka and the Kd involved in things, not just one rate constant, you got two. And so you can try that for yourself. That's why you get a T squared underneath there. And prove to yourself if you want. Just you get bored, don't have anything to do at the end of the age, right? If you're sitting in the airport or something waiting for a flight, just think, oh, the Arrhenius equation, K is equal to A, E to the EA over RT, and there's a Ka and a Kd equals big K, so how would that work? We took the natural log of the big K, which is the ratio of these, and, just do fun stuff like that to kill time. You don't do that?
Is that what you do?
Sometimes. Is it okay? You wonder, it could be, and you work it out. And sometimes you get close and you make mistakes and you check what the other people did. Oh yeah, I see what I did wrong there, right? That's so much fun. Yes, and then your flight's going to come, right? So it's good. Yeah. Better than checking out the vending machine, which has, expired potato chips in it or something. All right. Yes. Okay. All right. Oh, I'm sorry about the watermark there. Still trying to get my dossier fixed here all the way. All right, so what have we talked about today? We talked about the Langmuir isotherms, the Van Hoff equation, yes, for isosteric enthalpy of adsorption. Okay, what's isosteric mean? Iso means same, and steric. Well, I didn't think so. But here, I don't have it there anymore. I lost it, okay? But you're under constant what conditions? Pressure. Yeah. You might say isobaric almost, but they say isosteric, okay? All right, so you have some, I think you have a homework problem where you have a plug and chug to do with the Van Hoff equation. Maybe you have to plot something out, measure a slope, and then try to calculate what the delta H is for the adsorption there of some species on a surface. Okay? All right? So, that's it for all we got to do today. Those are the last few topics there. Everything else is from before. So I gave you a list of topics for test 4 a few days ago. You guys still have that? Okay. On Canvas? Probably not. If you send me an email, I'll try to remember to put it up there or email it to you or something. Yes? So I'll work from that to make your test. Your test is pretty much made up, actually. I had to tweak it a little bit here or there, but it's pretty much done. And that'll be a 100-point test. Winner take all, double or nothing type of thing. None of this take-home stuff, right? Do it in class. When it gets to be, 2:55, that's it, right? Day is over. The age has come to the end. It's time to get in your time cart and get out of the restaurant at the end of the universe, because everything is coming to an end. Yes? No, you didn't read those books. No, they're not really that good of books. They're kind of sacrilegious in many ways. But they have a big impression on you. There's some fun discussions about God in there, different points in time. But yeah, been a long time. They made a movie about those books, didn't they? Yeah, that's so terrible. They're always bad. I will not watch movies about books that I've read because they're always bad. Went to the Hobbit movie and it was just awful, right? Yeah, all it was is this dragon flying around in a cave, chasing everybody around. I mean, that's not what the book was about, right? Yes? Yeah, just terrible. Okay, so that's it, guys. Next time we'll be together, we'll be on Wednesday for test number 4. If you've got other stuff you need to get to me, get it to me soon. I think I've graded everything that I've gotten from you. Okay, so if you don't have a grade for something, it's because I don't think I've got it. Right? So if you want to get a grade for something that you don't have a grade for, best hand it in, okay, so that I can grade it. Yes? And it's much nicer to grade things all in one pool than dribbling in. Yes? Doesn't make me happy, and an unhappy grader makes for a lower grade. Yes? So keep your graders happy, right? And things in on time. So Friday, what's due on Friday? Well, what specifically was mentioned here? Yeah, your Jack of Shadow thing, okay? Because I'm not going to be reading those in June when you send them to me by email or something, right? Okay? Let's go back to that.
Now I have an idea.
All right. So, there you go. Friday. You're too late by then. My grades are due Friday after the end of the exam week, I think. So, yeah, for all you seniors, right? So get these things in.
Well, not this Friday, next Friday.
Next Friday, yeah. Yeah, after the finals.
Yeah.
Yeah, that would be a scandal. Yeah, all your grades are in before the final. Yeah,
yeah.
I just, think I look at you and say, oh, you're going to get that grade, and that's what I'll give you, right?
Hey, if
Yeah.
I'm okay with my grade before the final, I might just be like, that's it.
Yeah. Well, I should look at it as an opportunity, right? Yes? Okay, so I want good things on Jack of Shadows here. Don't just give me a book review and a summary of what happened. Jack ran into a stone and sucked the life out of it or something like that. I know all that, right? I've read the book. Yes, I want something, some interpretation, some symbolism that you gleaned out of here that isn't, obvious.
Did you list
to me.
the requirements for it?
Did I? No. I just told. Yeah. So give me something new and fresh and interesting.
So when I was in high school.
Yeah, whatever it takes. Yes, make it good, right? Yeah, That's right. So it's got to be good, right? Don't just knock off, requirement things. Make this something good, right? There's a lot of stuff in that little book that you could talk about, right? Pick something that's worth talking about. A character or a theme, right? Yes. Right, the machine at the end, at the center of the universe or the center of the earth. What does that represent? Right? Yes. How does that work? Right? What's he doing when he breaks the machine? Right? How does that affect the whole world in some way? Yeah. So you haven't read the books? Oh man.
He's just giving everything away. What's the
Wow.
point?
Well, you guys got to read the book and then tell me about what that means, right? I'm not telling you anything. That's just plot. You got to go beyond plot, right? You got to give me depth. Yes. Right? That's what I'm looking for. Right? Depth. Deep, meaningful stuff. Right? Stuff that makes them go, ooh, that's good. I like that. Man. That's what I want. I don't want to, they read the book. That's no fun. Yes? Right? I mean, I can do those every year and get the same papers every year. I want something new and exciting from you. Right? Yes? Are you with me on that?
Yep.
Okay. All right, so, go find your English major friend, right? Read them sections or something and see what they can come up with, right? Yes, something like that. That'd be good. All right, so that's the end of class today and the end of our formal lectures. Friday we'll meet again, go over anything on test number 4 that might have come up, and party up with donuts and stuff, right? Okay? So you don't have to eat lunch on Friday. Just come hungry for donuts. Yes? Okay. And I hope you don't get a sugar rush afterwards.